Welcome to our exploration of magnetic order in solids. Magnetism is a fundamental property of materials, arising from the behavior of atomic spins. In solids, these spins interact in various ways, leading to distinct magnetic phases. Understanding these phases is crucial for both scientific research and technological applications. Today, we'll journey through the main types of magnetic order, from simple alignments to complex arrangements, and discover how scientists study them using neutron scattering. Let's begin by looking at the most familiar magnetic phase, ferromagnetism. The ferromagnetic phase, neighboring spins prefer to align parallel to each other. This means that all spins point in the same direction, creating a strong collective magnetic moment. Ferromagnetism is what gives materials like iron their familiar magnetic properties. When you see a magnet sticking to your refrigerator, you're witnessing ferromagnetic order in action. The diagram for this phase shows all arrows pointing up, representing aligned spins. This simple yet powerful arrangement forms the basis for many everyday magnetic phenomena. Not all magnetic materials behave like ferromagnets. In antiferromagnetic phases, neighboring spins prefer to point in opposite directions. This antiparallel arrangement means that spins alternate between up and down, effectively canceling out the overall magnetic moment. The diagram for antiferromagnetism shows alternating arrows illustrating this pattern. Antiferromagnetic order is common in materials such as manganese oxide and plays a vital role in advanced technologies like spintronics. The exact arrangement depends on the crystal lattice, which we'll explore next. Two-dimensional square lattices and three-dimensional body-centered cubic (BCC) lattices, antiferromagnetic order can be neatly divided into two sublattices. One sublattice contains all up spins, while the other contains all down spins. This clear separation makes it easier to visualize and study antiferromagnetic behavior in these structures. Such arrangements are often found in crystals with simple geometric patterns, allowing researchers to predict and manipulate their magnetic properties for various applications. Face-centered cubic (FCC) lattice presents a more complex scenario. Unlike square or BCC lattices, FCC structures cannot be simply split into two sublattices. Instead, spins are parallel within certain planes, specifically those normal to the 111 axis, but alternate in sign from one plane to the next. This intricate arrangement leads to unique magnetic behaviors and challenges for scientists studying these materials. FCC lattices are common in metals like copper and nickel, making their magnetic properties especially relevant. Magnetic order isn't limited to just ferromagnetic or antiferromagnetic phases. Many materials exhibit more complex spin arrangements, resulting from subtle interactions within the crystal. These states include ferromagnetic, canted, fan, and helical phases. Each represents a unique balance between competing forces, such as local crystal fields and neighbor interactions. Understanding these complex orders is essential for developing new magnetic materials and technology. Ferromagnetic order is similar to antiferromagnetic, but with a twist. In ferromagnetic materials, the spins are antiparallel, yet their magnitudes differ. This means the opposing spins don't cancel out completely, resulting in a net magnetic moment. Ferromagnetism is found in materials like magnetite, which is used in magnetic recording and data storage. The unique properties of ferromagnetic phases make them valuable for both scientific research and practical application. Canted and fan phases arise when local crystal fields and nearest neighbor interactions compete. In these states, spins are not perfectly aligned or anti-aligned. Instead, they are tilted or form a fan-like pattern. This subtle arrangement leads to partial magnetic moments and can influence the material's response to external fields. Canted and fan phases are often observed in complex oxides and are important for understanding magnetic transitions in solids. Helical state is a fascinating example of magnetic order. Here, spins rotate in a spiral fashion, forming a helix. This occurs due to competition between nearest neighbor and next nearest neighbor interactions. Helical spin states are found in certain magnetic materials and can lead to exotic phenomena such as multiferrocity. Studying these states helps scientists uncover new ways to control and utilize magnetic properties in advanced devices. Study magnetic order in solids. Scientists use neutron scattering. Neutrons possess both spin and a magnetic moment, allowing them to interact with the electron spin density and atomic nuclei in materials. This makes neutron scattering a powerful technique for probing magnetic structures. By analyzing how neutrons scatter off a sample, researchers can reveal the underlying spin arrangements and gain insights into the material's magnetic properties. Effectiveness of neutron scattering in studying magnetism is quantified by the magnetic scattering cross-section. This value is proportional to the square of the magnetic scattering length. Denoted as P, the cross-section provides a measure of how strongly neutrons interact with the magnetic structure of a material. Understanding this relationship is key to interpreting neutron scattering experiments and extracting meaningful data about magnetic order. Formula for the magnetic scattering length P involves several factors: the neutron spin Sn, the magnetic moment factor V, and the Fourier transform of the magnetization MQ. The expression also includes terms related to the nuclear scattering length B. Typically, the magnetic scattering length is smaller than the nuclear scattering length, but both are essential for understanding how neutrons interact with materials. This formula guides scientists in designing experiments and interpreting results. Neutron scattering relies on the interplay between the neutron spin and the magnetization of the material. The neutron spin interacts with the electron spins, revealing the arrangement and strength of magnetic order. By measuring the scattering patterns, scientists can reconstruct the spin structure and understand how different phases emerge. This technique is invaluable for studying both simple and complex magnetic states. Magnetic order in solids has far-reaching applications. From data storage and magnetic sensors to advanced computing and medical imaging, understanding magnetic phases enables innovation across industries. Scientists continue to explore new materials and spin arrangements, unlocking potential for future technologies. The study of magnetic order is not just theoretical, it's a driving force behind many modern advancements. We've journeyed through the fascinating world of magnetic order in solids, from ferromagnetic and antiferromagnetic phases to complex spin states and neutron scattering techniques. Each phase offers unique insights and opportunities for scientific discovery and technological progress. As research continues, new magnetic materials and applications will emerge, shaping the future of electronics, computing, and beyond. Thank you for joining us on this exploration of magnetism in solids.